Alright, so here are two primary definitions for this set of videos. Given two groups G and H, a homomorphism is a function whose domain is G and whose codomain is H, satisfying the property that phi of G times H is phi of G times phi of H for all G and H in the domain. The other definition we're going to need is the kernel of phi, which is defined to be those elements in the domain whose image under phi is the identity element in the codomain. So all G in the domain group such that phi of G is the identity. We'll prove in class that this is actually a normal subgroup of G. But here I'm given the two definitions at once because as I run through my examples, we're going to show things are homomorphisms and we're going to compute the kernels for each example. Whereas the textbook defines the homomorphisms first and looks at examples, then defines kernel and then goes back and redoes the examples. My first example is actually not in the book. It's to connect this course to a previous course. So one example of a homomorphism you've already seen is an isomorphism. Every isomorphism satisfies that property. And you can check that the kernel of an isomorphism is the trivial subgroup. Another example of homomorphisms that you've actually seen in a previous course comes from matrix multiplication. So let R to the n and R to the m be groups under addition. So they're actually vector spaces, but let's forget scalars for right now and let's just talk about vector addition. So under vector addition, these are both groups. They're abelian groups whose identities are the zero vector, and the inverses is the negation operation. Let A be any m by n matrix. Then you can define a linear operator or a function from R to the n to R to the m by saying phi of x is equal to A times x. Well then, you can check that phi of given any two vectors x and y and R to the n, phi of x plus y, that's just A of x plus y. One of the features you learn in linear algebra about matrix multiplication is it distributes over vector addition. So you have A of x plus A of y. Well, that's just phi of x plus phi of y. And so in linear algebra class, we say phi is linear because not only is this true, but if you multiply by scalars, a corresponding property is true. But for our case, we don't care about that. We only care about this feature. So it turns out phi is a homomorphism. So linear operators are in fact homomorphisms. So you can see homomorphisms are a generalization of linear operators where you just forget about the notion of scalars. You're only talking about the binary operator. Phi of the binary operator applied to two inputs is equal to the binary operator applied to phi of the two inputs. And in this case, because the binary operator is addition, I'm using plus. What is the kernel in this case? Remember, it's all elements in the domain such that phi of that element is the identity element in the codomain. In our case, our domain is R to the n. And the identity element in the codomain is called the zero vector. So you're looking at all vectors such that phi of x is equal to 0. So you're looking at all n vectors such that ax is equal to 0. In linear algebra, they call that the null space. So the kernel can be viewed as a generalization of a null space. It turns out that linear operators are not the only homomorphisms you studied in linear algebra. There's exactly one other example, the determinant. So this is true in general, but I'm only going to focus on 2 by 2 matrices. So define the function from the set of all 2 by 2 matrices with non-zero determinants to the non-zero real numbers by sending a matrix to its determinant. We're going to let capital A and capital B be two 2 by 2 matrices. Here is A. And here is B, which, as you can guess, means that these entries are real numbers, and moreover, AD minus BC is not 0, and A prime D prime minus B prime C prime is not 0. So what do I need in order to say that this is a homomorphism? I need to check that the determinant of the product of the matrices is the product of the determinants. Now, I actually already did this calculation earlier in the semester, but that was so long ago, I'm going to go ahead and do the calculation again. So, determinant of the product of the two matrices. Well, first let's compute the product of the two matrices. Here it is. Row times column is AA prime plus BC prime. First row times second column is AB prime plus BD prime. To get this entry, it's the second row times the first column. So it's A prime C plus C prime D. Technically, I should say it's CA prime plus DC prime, but I'm going to keep things in increasing order by label because that's going to help with the calculations. Keep myself straight later. Finally, second row times second column is B prime C plus DD prime. What's the determinant of this matrix? It's the product of the diagonal entries minus the product of the anti-diagonal entries. And now you get the wonderful pleasure of foiling the first term. First, outer, inner, last. And then foiling the second product over here, the second binomial. First, outer, inner, last. Remember that there's a minus sign, so all of these are negated. And then we see that these first and last terms actually cancel. And what are we left with? A prime, D prime. Plus B prime, C prime, minus B prime, C prime, D, minus A prime, B, C, D prime. On the other hand, if you look at the determinant of A, it's AD minus BC. The determinant of B is A prime, D prime, minus B prime, C prime. If you FOIL this, the first term is here. The last term is here, and the outer and inner terms are these two. So you do in fact see the product of these two determinants is the determinant of the product. So you do see that we have a homomorphism. In fact, this actually works even if I remove the 0 here and I take all 2 by 2 matrices. Nothing in this calculation required me to assume that the determinants are non-zero. The only difference there is that in that situation this isn't a group because 0 is not invertible. So we kind of want to avoid that for right now. Alright, so now let's compute the kernel of this function, which I was calling phi. So textbooks like to use phi, but you'll often find later I will actually just go ahead and refer to certain special homomorphisms by their preferred names. This function has a well-defined name. It's called the determinant map, so you might as well call it the determinant map. What is the general definition? It's all elements in the domain such that the image is the identity element in the codomain. What does that mean in this case? Well, what is the domain? The domain is the set of invertible 2 by 2 matrices. So an element in the domain should be a matrix A. My function is the determinant. What is the identity element in non-zero real numbers under multiplication? It is the number 1. And so that's what this kernel is. Earlier in the course, this actually got its own special name. It was called the special linear group. And so it's all matrices of determinant 1.